Hi all. Right. This is quite exciting for me. Right. Sorry, I'm boring. I love numbers. But numbers are important for us to understand how numbers fit into our lives. And this is the number system. We're going to be dealing with real numbers in this little video. We're not going to be dealing with imaginary numbers. And there are such things as imaginary numbers. We'll get to that certainly at a later video. So looking at numbers, let's figure out how numbers actually came into being used in our language, right? Initially, people counted things, right? These are called natural numbers. These are called natural numbers. People counted things, and they said, wow, we can count things, right? So I've got a number of rocks in my cave. 1, 2, 3, 4, 5. They were natural numbers. They didn't have a concept of having zero. Now, first of all, guys, listen to me carefully. There's a massive difference between zero and nothing, right? And we have the Incas and various other ancient people to thank, including the Egyptians, by the way, to thank for the discovery of the concept of zeros. Now, natural numbers were often called counting numbers, and it is the way that we count. 1, 2, 3, etc. upwards. Earliest man needed to count things. They needed to know how many things there were. There were 5 bisons on the field that needed to be hunted. Can we hunt 3 of them? Will we leave the females? Right? They needed to count, right? And that's really, really important. So these are called natural or counting numbers. And then people realized that, at some stage in our evolution, we needed to understand that there was a number called 0, right? And 0 was part of our numbering system. 0 is very different from nothing. Nothing means nothing. 0 means a number. And they then came up with a whole number system. 0, 1, 2, 3, 4, 5, 6, 7. There was not yet a concept of anything in between 1 and 3 or 0 and 1. And there was not yet a concept of negative numbers. But there was a concept in history of 0. And 0 is a very, very important number. 0 is not nothing. So, let's just recap quickly. Natural numbers were 1, 2, 3, etc. Right? And whole numbers started with 0. 0, 1, 2, 3, etc. But eventually we progressed in society and we needed to understand that there were negative numbers. Now most of this is attributed to the understanding of finance, where you could owe somebody money. So your net worth was negative. And we came up with integers. And integers were quite interesting. That said, right, we count whole things, all right? We don't count halves and quarters and thirds and 0.5s or whatever. But when we're counting whole things, we can have negative whole things. So we can go -3, -2, -1, 0, 1, 2, 3. And those were called integers. Now, all of a sudden, people started understanding, hey, but you could split a dollar into its cents, so it wasn't a whole dollar anymore, right? So you could have you could owe a $0.50 or have minus $0.50, or you could have a third of a dollar, or own a $0.50, or own 3 2/3 dollar, right? And these became rational numbers. So all of a sudden, between these whole integers, we could now go and fill in minus a half, which would be somewhere there, a third, which would be somewhere over here, between 1 and 2. Those were the rational numbers. And lo and behold, mathematicians started fiddling around with life and found out, my goodness, there are things called irrational numbers. And there'll be more about this there. And probably the most famous irrational number of all is a number called pi. And when we do the geometry series, you'll understand how pi was discovered and why it was discovered and why it's irrational. Right. So let's have another way of looking at this. Okay. So we started off and we said, right, we can count things. Ancient man could count things. So they started 1, 2, 3, 4, 5, 6, 7, 8, 9. And these were real numbers, or what sometimes are called counting numbers. But they're discrete points along a line. And let's just visualize it as this, because we're building up towards understanding numbers in a line. Right. So now let's get this along the line. Whole numbers included 0. So whole numbers were 0, 1, 2, 3, 4, 5, etc. Right? Off into infinity somewhere over here. All right, but they were whole numbers, they were discrete numbers, and they were points along a line. Okay, and the whole numbers evolved into the concept of integers, right? And integers were whole numbers but included the negatives. So they were just like the whole numbers, excepting they included the negatives. So -6, -5, -4, etc. up to 0, 1, 2, 3, 4, 5. Now I've left the colors over here red as indicating the counting numbers, right? Or the real numbers. Well, these are all real numbers, so the counting numbers, right? And I've left the little 0 as the white number, the whole numbers, and the integers have come along, right? And our number system was nearing completion, right? So if we now just assemble these all as integers, right? Let's assemble these all as integers. As such, right, there are gaps in our understanding. Where does a half fit in? How do we indicate a half? How do we depict a half? How do we make a half visible to people? How do we understand what a half, a third, a quarter, 2 1/3 is, 5 and 7/10 is, for instance? Well, we needed to be rational, and to be rational we needed to put things on a line, right? And this is just a way of visualizing it, but the concepts are what's important here. So rational numbers say, hang on, we can understand all numbers written as a upon b, where a is an integer and b is an integer, but that we can define. All right? So rational numbers, for example, can be 1/4 or 1 upon 4, and that is equal to 0.25 exactly on the line. So we can indicate a quarter exactly on the line, and it's here somewhere. So the quarter is there somewhere, and that's a rational number because it can be written as a upon b or something upon something else, and where both of those somethings are whole numbers and can be exactly found. The exactly concept is important here, right? So taking this to the next step, so 29 upon 4, right? Okay, so how much is that? Right, and 4 goes into 29 7 times, and it remains 1/4. So it is 7.25 exactly, and we can we are able to pinpoint this exactly on the line for ourselves. We are able to pinpoint this exactly on the line for ourselves. Right, but then there were some very interesting numbers that came along. Numbers that could be written as a upon b often, but they cannot be found exactly. We cannot pinpoint them. And these are irrational numbers. And mathematicians were more famous for discovering these numbers and finding them, right? And one of the most famous, as I said earlier, was pi. Now, pi is written as a upon b, 22 upon 7. Pi is 22 upon 7. And pi has got something to do with circles, and that you'll understand in our introductory to geometry environment. 22 upon 7 can be written as a upon b, but guess what? We cannot determine it exactly. So if you take out your calculator and you take 22 and you divide it by 7, it'll probably show you something like this. Right? And it's not exact because it carries on for decimals. Now there are some computers in the world that are still trying to find the value of pi, and they've gone into millions and billions of decimal points. But it cannot be determined exactly. Right? So, the wonder of pi, right? Pi is irrational. It's 22 upon 7, but it cannot be found correctly. Now, I've indicated about 250 or 300. I have indicated about 200 or 300 decimals over here for pi. You can go and Google this, right? There's a famous site that displays 1,000,000 decimals of pi. Pi is a very interesting number. It's great fun to actually think about the fact that there's a number that is real, but it is irrational. And that is the real number system. Thank you very much.